The topic is magnetic field along the axis of circular current carrying loop. So this is important question asked many times in the final exam. Many times. So concentrate well. So the magnetic field along the axis of the circular loop that is carrying a current. That means I have a circular coil. I'm going to consider a circle only now. Okay, this is a circular coil and it carries a current. It is carrying a current. When it carries a current, what happens? It produces the magnetic field. What is the shape of the magnetic field? We already studied in earlier classes. The shape of the magnetic field is straight. For circular coil, the straight magnetic field you are going to get. That can be found by right hand rule. We already studied it. But now I will just turn this coil like this. Like this. So I just turn the coil so that the current come from outside the plane of the paper and comes inside towards me and again enters the paper. So inside and outside it goes. So here the figure is there, you can see. Now this is the axis where I am writing. This is the axis, the point at the center through which any line, if it is passing, that is called as axis of the circular loop. So here we have taken like this. This is a circular loop and this is the center of the circular loop and this is the axis. This is the axis. On this axis, this coil produces the magnetic field. And that magnetic field, we have to find it out. That is the aim of this particular derivation. So that's what the magnetic field along the axis of circular loop we are going to calculate. Okay. Now the figure is looking little complicated, but it is important derivation. You must practice it. So I'm going to draw the diagram properly. You can see how to draw the diagram. I have a representation, PPD representation over here. Okay. So the heading is the magnetic field due to circular loop carrying current. I am going to calculate the magnetic field at a point on the axial line. So let us draw the diagram. So let me consider a coil. This is a coil and the center O. The radius of the coil is A and the current is I. The current flowing through the coil in anti-clockwise direction, that is I. Let P be a random point we are considering that should lie on the axis of this particular coil, where I am going to find out the magnetic field. So this is the axis and the distance from the center of the coil to this particular point P is X we considered. Now I will consider one more line. This is from one edge of the circular loop to somewhere at point P. I will call this as R. So that the angle between the circular coil and this line R, which is 90 degree. It makes an angle which is 90 degree. So the angle which is making with this one here, this should be 90 degree you are going to get. Okay, remember that 90 degree, we will use that later. So DL is the small current element. That means only this portion here having length DL. And the current which is passing somewhere here, it is coming, I is coming, and comes out of the plane of the diagram or plane of the figure towards me. The current is coming towards me, and it just goes here, and it enters and goes out of the plane of the figure, plane of the diagram, away from me. It is going away from me. So it is coming towards me here, and it is going away from me. So cross I'm going to show. So the figure, how it is there, it is not like this. I just turn this circular coil like this, so that this part this part is outside the plane of the figure, and this is towards me, this side is towards my side. Okay, this is how I consider the figure. Okay, now this is dB. dB is the magnetic field produced by this current carrying element, small element. This element produces the magnetic field at point P. The direction of magnetic field at point P due to this particular element dl is in this direction. And how to find out the direction of magnetic field? We can find it out by using a right hand rule. Here you can see I have a right hand rule to apply. I will just show that. I will use the right hand. I will bring the right hand now here somewhere. I am going to curl my finger from where to where? From DL towards R. Why? Because of Biot-Savart's law, right? We studied Biot-Savart's law. There, what we studied, the magnetic field direction can be found by using DL cross R. So we have to curl our finger from DL towards R. So here DL is somewhere here. You can see DL, and I'm curling my finger from DL towards R. R is downward here, right? So then you will get the magnetic field direction where the thumb points. So I'm curling my fingers from DL towards R. So the thumb points in this particular direction. That's what you are observing here. So this is the direction of the magnetic field. That's what we have taken it here. So we have to apply a right hand rule. So this is three-dimensional diagram. You can imagine you have to curl your finger from DL, the direction of DL, towards R. R is downward. Then thumb points in this particular direction. So that is the direction of dB. That's what we showed it here. Okay, next we will continue this, the same presentation. Okay, we wrote here. So magnetic field direction we got from rule, this particular rule, right hand rule. We applied it. So thumb, where it is pointing, the same way the magnetic field is pointing. Let phi be the angle between R and X. Now what I am going to do, this dB is a vector. It is a magnetic field. It is a vector. Any vector can be resolved into two rectangular components, right? So dB cos alpha in this direction and dB sin alpha perpendicular to that. We studied it in the first PU, motion in a plane chapter, motion in a plane. So dB cos alpha or cos phi you will get in this direction, because phi is somewhere here, that is why cos alpha term, and dB sin alpha term here you are going to observe. Next, one more term I'm going to consider here, small element dl. This is also having the same length as that of xy. So the current comes here and enters towards D into the plane of the paper, goes out of the paper, comes towards me and goes out of the paper, comes inside towards me and go away from me like this. So again, if you curl your finger from DL towards R, so R is this one, this particular dotted line. So if you curl your finger from DL towards R, then where the thumb points? The thumb points in this particular direction, downwards. We will see that. So like this. Again, this dB is a vector quantity. We can resolve them into two rectangular components. So dB cos alpha and dB sin alpha. In a figure, you can see dB cos alpha and dB cos alpha are equal in magnitude but in opposite direction. Therefore, they will cancel each other. But dB sin alpha and dB sin alpha are in the same direction. Therefore, the total magnetic field will be gets added up. Because of these two length element at C and D, we are going to get dB sin alpha and dB sin alpha 2. For from two elements, two magnetic field you are going to get. That should be along the axis you are going to get. That is not perpendicular to the axis. Perpendicular axis, here you see this magnetic field will be cancelled, but along the axis the magnetic field will be added up. So from two elements you are going to get 2 dB sin alpha, sin phi. Suppose if you see the diagram, there is not only DL and DL, two DLs. To make this complete circular loop, you need many such DLs. So here also DL is there. One more DL I will consider length, and here also DL is there, right? Here also DL is there. There are many such DLs together forms the complete loop, and the current is flowing through all these DLs, and all these DLs will produces the magnetic field at point P. So each DL will produces its own dB sin phi, its own sin phi that should be acting along this particular direction. So we have to add it up. How to add it? We can use either summation or we can use the integration. We will see that later how to do that. Okay, the figure here, the plane of the coil is considered perpendicular to the plane of the diagram. It is not like this. The circular coil we have considered not like this. It is turned so that it is perpendicular to the plane of the figure, plane of the diagram. Okay, such that the direction of magnetic field can be visualized on the plane of the diagram. See, this dB and dB are visualized along the plane of the diagram. It is not into or outside the plane of the diagram. Okay. At C and D, current elements xy and x dash y dash are considered such that current at C emerges out, that is coming towards myself, and at D it enters into the plane of the diagram and goes away from me, away from the observer. Now we understood how to draw the diagram. The diagram only took some more time, but derivation is so simple, right? Only few steps are there. Okay, only few steps. Try to understand these steps now. So after drawing the diagram, so the current is flowing through this coil, and this part is outside the plane of the paper I am writing, and this part, this portion is inside the plane of the paper. That means the current is coming from outside the plane of the paper and coming towards the observer, myself, and it enters the plane of the paper and goes away from the observer like this. So when the current is flowing through this small portion of the conductor A of length dl, it produces the magnetic field. It produces the magnetic field at point P, somewhere here. And that magnetic field, small magnetic field, can be found by using Biot-Savart's law. According to Biot-Savart's law, dB is equal to mu naught divided by 4 pi I dl sin theta divided by r square. Just have a look at the previous video, that is Biot-Savart's law. And this magnetic field is acting in this particular direction as explained in the figure. Theta is equal to 90 degree as explained in the figure. Therefore, sin 90 becomes 1. Sin 90 becomes equal to 1. Therefore, above equation can be written like this. dB is equal to mu naught divided by 4 pi I dl divided by r square times 1. Sin 90 is equal to 1. Now one more portion I am going to consider at the bottom of the figure, somewhere here. And the length of this element is also same, dl. So when the current is flowing through this dl, that also produces the magnetic field at point P. And the direction of that magnetic field is downward. We can tell you how it is downward because of a right hand rule. We have to apply the right hand rule that gives the direction of magnetic field downwards from this element dl, and the magnetic field remains same by Biot-Savart's law. dB is equal to mu naught divided by 4 pi I dl sin theta divided by r square, no change. Again, theta is equal to 90 degree. If theta is equal to 90 degree, sin 90 is equal to 1. Therefore, the equation similar to this equation you got. This equation and this equation, you see, both are exactly similar. Magnitude wise, both magnetic field are exactly similar. But direction wise, this dB is in this direction and this dB is in this direction. Okay. Now I want to calculate the total magnetic field at point B, at point P. Here we found the magnetic field at point P due to only these two elements at A and B. But this coil consisting of many such turns, this coil consisting of many dls. This is a dl here, and here also there is a dl, and here also there is a dl. There are many dls, right? All these dls will form a complete circular loop. When current flowing through such a loop, all these produces the magnetic field at point P, and that total magnetic field at point P can be given by this dB sin phi should be added. So 1 dl will produces 1 dB sin alpha. One more dl will produces 1 more dB sin alpha. If all these dl produces 1 dB sin phi, then total dB sin phi can be found by integrating that. So the total magnetic field at point P is B is equal to integral of dB sin phi. What about sin phi from the diagram? Look at the diagram. I will erase it first. So from this triangle AOP, in this triangle, what is sin phi? The sin phi is equal to opposite A divided by hypotenuse R. So that's what we wrote it here, A divided by R. And dB is equal to, as it is, we took it here, dB is equal to mu naught divided by 4 pi ideal divided by r square. Now take this particular equation and substitute these two values into this equation. So what you will get? So dB is equal to mu naught divided by 4 pi ideal divided by r square, and sin phi is a divided by r. In this equation, take the common terms. Except dl, all are constants. You take it out of the integration sign. So you will get this equation. And what is this integral of dl? The integral of dl. Integral of dl means you just have a look at the diagram. There is a loop. How this loop is formed? This loop is formed because of there are many dls should be integrated. So one dl, one more dl, one more dl. There are many dls. One more dl, dl. So all these dls will together form a loop, and this loop can be formed by integrating all the dls. Integrate means adding all these dls. So adding all these dls, you will get entire circumference of the loop, circumference of the circular loop. Therefore, if the radius of this circular loop is a, then 2 pi a. That's what I'm using it here. Therefore, similar terms you can cancel it. 2 with 4 will get 2 here, and mu naught I, this a and this a will be a square and r cube. Pi and pi also cancelled over here. So this relation you got it. But now I want to substitute the value of r. What is the value of r from the figure? So you see this one r. Apply Pythagoras theorem to the same triangle AOP. So r is equal to square root of a square plus x square, right? So that's what I'm using it here. So r is equal to square root of a square plus x square. So substitute it here. So mu naught I a square as it is divided by 2. R value is x square plus a square to the power half. 3 as it is, you keep it here. And this is the final relation. This is the final relation of magnetic field at a point P. So I will write it once again properly. The magnetic field at a point P along the axis of circular current carrying coil is equal to mu naught I a square divided by 2 times x square plus a square to the power 3 divided by 2. Mu naught, permeability of free space. That means the coil present in air or vacuum, and I is the current flowing through a coil. A is the radius of the coil. X is the distance where we are finding the magnetic field from the center. So this distance x from O to P. So this is the final step, that is the magnetic field at point P due to circular current carrying coil. The derivation is easy and you know how to draw the diagram. For explaining the diagram only took a lot of time, but the derivation is simple and the derivation is most important. So almost every year the question asked. So practice this derivation. So the final step we got is B is equal to mu naught I a square divided by 2 times x square plus a square to the power 3 by 2. So this is the magnetic field along the axis of circular current carrying loop. So the same diagram I will just copy it and paste it here. Okay. So here we found the magnetic field. The magnetic field at this particular point due to this entire circular coil. So that equation we got it here. So what is here mu naught? Mu naught represents this coil is present in air or vacuum, and I is the current flowing through this circular coil, and A is the radius of the coil. And what is X? X is the distance where we are finding the magnetic field from the center of the coil, from O to point P, that is X. So all are there. Now there are some special cases I'm going to consider. The case 1, if the coil, same coil consisting of n number of turns. So there are many such turns, 1, 2, 3, there are n number of turns. Then the magnetic field at point P increases. How many times it will increases? It increases by n number of times. That's what the same equation we wrote, but we included one more term, that is n. So to produce the magnetic field at the center of the coil or along the axis of the coil, you need more number of turns. This is the case 1. And case 2, I will consider the case 2. Suppose I am going to take this point P at the center. Suppose this point P I am taking it somewhere here at the center O, then what is the value of X becomes? So the X value decreasing. When I take the point P somewhere here, the X value becomes 0. So X value becomes 0 at the center of the circular coil. Once the X becomes 0, so this value becomes 0, then how the equation looks like? So mu naught n I a square, the numerator is same, denominator x becomes 0, so 2 times a square to the power 3 by 2, and 2 will be cancelled, and you will get mu naught ni divided by 2a. And this is the magnetic field at the center of the circular coil. Exactly at the center, the magnetic field can be calculated by using this relation, mu naught ni divided by 2a, n number of turns in it. And what should be the direction of magnetic field? The direction of this magnetic field can be found by using a right hand thumb rule. As I told in the first class itself, in the first video, earlier video, the same rule I applied. You see, if the current is going in the figure, you're observing current is in this direction, then curl your finger in the direction of current, and where the thumb points along the center, along the axis. So this is the direction of magnetic field. So the magnetic fields are in this direction, means it's supposed to be north pole this side, and here it should be south pole. For the observer standing here, it appears like north pole, and for the observer standing here, it appears like south pole for them. So this is the direction by using right hand thumb rule.